All right, welcome everybody. Good afternoon. We're very glad you decided to join us. My name is Mike Cassidy. I'm a professor in Berkeley's Department of Civil and Environmental Engineering. And at present, I also serve as the vice chair for undergraduate studies. I mention this because I think it's in that capacity that I have the pleasure of participating in today's event. Now, with regard to that event, as you might imagine, what we want to do here is we want to try to familiarize you with Berkeley's Department of Civil and Environmental Engineering. Our real goal is to give you the best sense possible of what our civil and environmental engineering program has to offer junior transfer students such as yourself who are considering maybe joining our department. First thing I want to say about this is that our department features a very large number of areas of expertise. And these areas include structural engineering, geotechnical engineering, environmental engineering, systems engineering, transportation engineering, and finally, engineering project management. Now, today, in our effort to familiarize you with some of these distinct programmatic areas of expertise, we're going to talk about some of the courses we teach. And these courses collectively span most of those areas that I just mentioned. I should also mention that the courses we're going to talk about today are all what we call upper division undergrad courses. What that means is that should any of you ultimately decide to join us, those courses would automatically be open and available to you on your entry into the program. Now, the best thing I can say about today is I don't come here alone. To the contrary, I'm joined by 6 colleagues in the department, including 5 professors who teach some of the courses we're going to talk about today. So let me start by very briefly introducing the faculty who are with us. We have Professor Ada Athanasopoulos, sorry. Sorry, Ada, sorry about that. I was practicing all day, although you couldn't tell. Okay. We also have Tracy Becker, whose name is very easy to say. We have Professor Kenichi Soga. We're also going to be joined by Professor Mark Stacy, who is the department chair. And shortly, we'll also be joined by Professor Cara Nelson. And also, I'm very happy to introduce Julia Kanopasek. Julia is our department's undergraduate student advisor. So, okay, what we'll do is each of us will speak for 5 minutes about a course that we teach. And then after we finish these brief presentations, we'll kind of throw the floor open for any questions you might have about these courses or about anything involving our program that might be of interest to you. So without further ado, why don't we start with our first presentation? I think, Kenichi, you'd like to go first?
Yeah, if you think it's okay, I'll...
Yeah, very okay. Yeah. You think it's okay?
Yeah,
okay.
Yeah. So let me share my screen. Okay, here we go. So the class I teach is called CE 170A, Infrastructure Sensing and Modeling. This course started 2 years ago. This is our 2nd year of teaching. The spirit of this particular course is that the future of infrastructure relies on smarter information. The rich information obtained from embedded sensor within infrastructure and large-scale computer simulations will catalyze a new design, construction, operation, and maintenance. And really, to this particular course will teach fundamentals of various sensing and modeling tools for infrastructure engineering and present case studies. Also, there's a trend in entrepreneurship in civil engineering going on right moment, so we are discussing that. But before I go further ado, I thought I should give you this video which shows what we do. Just going to optimize the video, and then you'll see here. So hopefully that gives you some idea of what we do in this particular course. And you can see our students learn about model bridge with emergent technology and sensors and data analytics, and really do some engineering analysis, really understand the actual performance versus design assumptions to see what we design and then what is real. And then bringing some internship in civil engineering. So these are the companies. So like these are the companies that come and present their technology in the field of civil engineering. So that's all I have for my part. Thank you very much.
Thanks, Kenichi. Ada, how would you feel about going second on this parade?
Sure, I will bite the bullet and be the one to go after Kenichi's cool video. Thank you for that. So I did not have a production team for my class, but let's see. Okay. Can you see my screen?
Yes.
Okay. So the class that I'll be describing is C175, Geotechnical and Geoenvironmental Engineering. And this is the class where you first get exposed, introduced, and hopefully learn some of the fundamentals behind both geotechnical engineering and a little bit about geoenvironmental engineering. And so when we talk about geotechnical engineering, we basically describe the part of civil engineering that deals with natural materials that are found fairly close to the surface of the earth, which is what separates us from geologists and seismologists. We discuss basically the principles of soil mechanics and rock mechanics to a lesser degree, and how these affect the design of foundations, retaining structures, and earth structures. In addition, we include certain elements that would then lead towards future classes that focus more on geoenvironmental engineering. We discuss properties of soils that impact the way contaminants may travel within soils, or how we would be able to get them out as part of a cleanup in a contaminated site, and also discuss a little bit about remediation of these sites. So specifically, we want to basically teach you the fundamentals that you would then use to analyze problems such as slope stability problems, sinkholes, problems with settlements, foundation failures. So a lot of these that affect critical infrastructure and lifelines, and infrastructure that we all deal with on a daily basis. So transportation networks can be affected by such hazards, our own houses, pipelines, water networks, dams. All of these systems basically would need and require the really good understanding of the subsurface ground conditions before we're able to analyze what the problem is and how to fix it, or how to make sure we don't encounter it in future natural disasters, such as, as we recently see hurricanes or earthquakes and whatnot. So in terms of how the class tries to address that, we do focus, as I mentioned, on the fundamentals behind soil mechanics. So we start by studying the physical properties of soils. So this focuses on the mineralogy and specific characteristics that come with soils that then control what we study next, which is the mechanical properties. So how easy is it to compress some of the materials? How strong are they? And again, how that would relate to future analysis. We will look at hydraulic properties of soil materials, and then also discuss basically the laws, the soil mechanics and hydraulic laws that govern these relationships. In terms of how we normally go about learning about these things, that has, it's a multifaceted approach. And we won't cover everything in this class, but as you just saw in the class that was described before, observation and monitoring the behavior of existing infrastructure is a critical component in understanding how it may behave in the future. And so we do discuss case histories in the class. We also focus on experiments, primarily in the laboratory, but there's also a field component for future classes that this class would definitely prepare you for. And we can also look at how we can construct physical models that are in a smaller scale for geotechnical applications to better understand the full scale response. And finally, we do discuss the theory, as I mentioned before, the laws that would be behind numerical analysis. So this class, as I mentioned, focuses on some of these components, but definitely provides the fundamentals so that you can build towards the other components in other classes that you may take concurrently with this class or following this class. The other important thing to mention about this class is that it is co-taught between one geosystems faculty and our lab director, Professor Mike Reamer, who basically works in the laboratory sessions of the class. So the class does have both lectures, weekly lectures, and laboratory sessions. There are 4 sessions, so 4 of the weeks in the semester, you will have a laboratory session on a specific day. And the labs that we work on in this class deal with soil identification. There is a hydraulic connectivity test that we do, shear strength testing, and then also compaction. And these labs basically work in that most of them are hands-on, not just demonstration labs where you get to produce your own data and then summarize in a very short write-up / report, but it's not, I really don't want to call it a report because typically it's just a couple of pages, but so that you get to understand how to present information that's relevant to what you just did and that sort of thing. So with that, I will just drop my email here in case anybody has any follow-up questions for me later on and pass it on to the next faculty member. Thank you.
Thanks very much, Ada. Tracy, what do you think? You want to go next?
Yes, sounds great.
All right.
Let me, one sec. So I teach steel design course. And so let's do that. Oh, I don't think I can do full screen, but everybody can see. So I teach the steel design course, which is sort of a synergy between taking your mechanics background and some analysis background, and then getting to see where we can do and how we can bring that into the design world. So there's also another course that's in concrete, but this one's just focused on these systems. So this is actually Jacobs Hall. This is a building that's on campus right now. And you can see that we talk a lot about how our loads come through our structures. So things going from the slabs to the beams to the columns, how things are transferred to the ground, lateral load systems like wind and earthquakes. And so we bring that together and talk about all the forces on these different members and how we would need to design them. So for example, how we would design a brace for tension and compression, how we would design a column for compression, how we would design a beam for the bending that's going to occur. So all of these have different forces on them internally and make it have different failure mechanisms. So we have to consider all of those things in our design. So when we're going forward with this, it's nice to have some visual representation. So we go down in the lab and we do a couple experiments, just like you do in geotech, but here we're doing, steel components. So there's 3 major labs. We do a tension lab, so you can see that on the left. This is down in our main structural engineering lab that you can see behind me. And you can see fracture here at below the bolts in my tension test. We do some compression tests, so you can see a column that has buckled in our lab, and then we go and we work on these in groups and write these all up. And so it's important that we learn how to use the code and we learn what the code says, but we also learn what's behind the code, because the code is a living document. It's updated continuously, and our graduates need to be able to understand why there's something in the code and, be the leaders in the field when we need to change the code in the future. So it's important that we understand why, not just how to do it. Throughout the course, we work on a large capstone project with groups in the course. This is last year's project. Students designed bridges that were situated in the Oakland International Airport Terminal. So these are not real bridges, but a potential design. And so students put together professional design documents, produced all the plans for the bridge, did deflection analysis for the lateral earthquake loads you can see on the top right, and also did the individual designs for each component, each section of the bridge. So you can see the column design on the bottom right. And they put together some very, very nice professional reports, and it involves a presentation to help just to the other students to really help solidify the professional aspect that you'd have to be communicating all of this information to your team. So that's what we cover in steel design.
Thank you, Tracy. Thanks very much. How about we get our department chair, Mark Stacy?
Hi.
Nice to see you. On my attendance book says you were late.
Yeah, I'm sorry I was late.
Presentation will make up for that.
You can mark me down.
Okay.
Great to see everybody. I'm really happy that we have this opportunity to introduce you to some of our coursework. I think what you're seeing is a cross section of these upper division courses that we offer that would make up a lot of your experience were you to transfer to Berkeley to finish your degrees. What I'm going to speak to, and especially as Professor Soga was doing his bit, I was scrambling around trying to find some graphics and stuff. So I'll share my screen in a moment, but I'll apologize in advance. I'm in the process right now of creating and launching a new course that'll be taught for the first time this spring in the area of climate change adaptation. And if I can see, so I don't have my own video, but the web, can help with that. And so this is a nice graphical interface from The Guardian. And what I like about it is it lets you scroll through for different for different climate related impacts. So for example, heat waves first, you can scroll through and see, okay, if we can control global temperatures to within 1.5 degrees Celsius of historic, what do future heat waves look like? And then you can scroll to what does it look like if we hit 2 degrees, and then finally to 2.5 degrees. And you can see the spread of these annual sort of exposure to heat waves around the Southeast US and increasingly in the US West. And then if we go, other things that can be featured when we think about the impacts of climate change include floods. And so they have a similar graphic here to look at how current policies, but with a warming planet, what is going to be more susceptible to these large changes in precipitation as we warm the planet. And you can see that much of the South and West US is affected by these changes in precipitation. Some of it's increases, some of it's decreases. It's mostly about variability. And of course, wildfires is one that's been on all of our minds for a number of years, and you can track the change in the coming century. This is what's coming. As engineers, we have to continue to find solutions that work for today, but increasingly anticipate tomorrow. Anticipate tomorrow in a way that is sustainable and equitable and just, that ensures that everyone who is reliant upon those infrastructure systems or those other interventions shares in the benefits of them. So the course that I'm developing, and I'll just share my screen for the syllabus now. I don't have anything fancier than that, unfortunately, but is a course called Climate Change Adaptation. And the goal of the course is to understand holistically how we think about solutions and adaptation to climate change. And the way I've organized the course is into a series of modules, each one about 2 weeks in length. First module kind of just sets us all on the same page, thinking about understanding climate change. But one of the things that I want to emphasize is this interplay between the built infrastructure, the natural infrastructure, and the social systems, and how those three components define the future for communities, creates certain interactions and interdependencies, defines the local impacts of that global change. So that's all sort of this first unit, is get us all on the same page, so we're talking about these things in a holistic way that still centers the need to find engineered solutions, but with an awareness of how those engineered solutions interact with natural systems and with social systems, or perhaps leverage them in certain ways. Then we go through a series of modules that look at different future risks. For now, I've got drought as this next module for this next offering, this first offering. That might be replaced with one thinking about energy transitions and global mitigation, just because of how it fits in the curriculum this year. But then later ones, urban heat islands, understanding that heat island effect, understanding how different interventions like green spaces, novel materials, cooling infrastructure interact with the function of a city, and understanding the social norms and behaviors that exist within that. One of the readings that we'll do in this unit is from a sociologist, which is an analysis of a heat wave in the 1990s in Chicago that explored how the green infrastructure in the sidewalks and other spaces in these neighborhoods not only provided cooling, but also encouraged interaction and created a social infrastructure and a social network that helped improve outcomes during the heat wave in Chicago. So it's this interplay between the built and the social infrastructures. I won't go into details on all of these. I'm sorry, I'm taking a long time. We'll talk about wildfires. One of the themes here will be thinking about indigenous approaches to fire, where fire was a normal part of land stewardship, and thinking about how we've moved away from that especially at the urban wildland interface, where a lot of the wildfire threats emerge. We'll also talk about smoke and air quality risks associated with wildfires. Flooding, we're going to have two different units on flooding. One will focus on sort of precipitation-induced urban flooding types of risks. That's really going to focus on extreme precipitation events, imperviousness of the lands, how green infrastructure can address that, and thinking about interactions across different systems and how that creates cascading failures as one system fails, affecting the next. And finally, a unit on coastal flooding, where we kind of think about what's coming from the seas in the form of sea level rise, storm surges, rising groundwaters, and again, how that interacts with the natural and social systems. Within each of these modules, we'll have a combination of a couple different assignments. There'll be a sort of a traditional engineering style problem set associated with each module, but there will also be a more, I'll say a more thoughtful writing piece reflecting on the interactions that are exposed in this module. So yes, it's about the engineering at the core of the course, but it's also about the things that go with it. And so there will be some writing and some calculations as a part of the course. And then finally, we'll finish this semester with some term-long projects where students will do a deeper dive into one or more of these particular threats and start thinking about actual interventions and solutions. So I'm super excited about this course. It's one that I've had kicking around in my head for about 5 or 6 years, finally taking the plunge to create it and launch it. And it will be offered this spring, and then in future years, it will probably be offered in the fall semester. I would expect for transfer students, probably fall of your senior year, the second year that you're here at Berkeley would be the sweet spot for taking this course. So thank you for the chance to share.
Thank you, Mark. I think that leaves me. I'll go next. So let's see if I can share my screen here. I want to talk about one of the classes I teach. That's called CE 155 with the title Transportation Systems Engineering. Now, I think we all understand that transportation is vital for society. When you think about it, transportation is really key to a community's economic well-being, as well as its livability. How pleasant is it to live in this city? But on the other hand, transportation also imparts a good deal of negative impacts as well. There are negative impacts in terms of public health because traveling can be dangerous. And of course, we know that transportation exerts negative impacts on the environment in terms of greenhouse gas emissions, fuel consumption, and so forth. The simple point here is that transportation engineering deals with problems that are especially important. But at the same time, these problems are very, very interesting and intellectually satisfying to pursue. And I think the reason for that is because these are kinds of problems that require very specific sets of technical skills, as well as just general creativity. These two elements are needed to kind of address the questions that transportation engineers try to deal with. And these are complicated questions. For example, how can we abate traffic congestion during the rush hour in a busy downtown? Or how can we design and lay out and operate a new bus route to serve society to the best way possible, while still duly considering all the costs involved? Other questions include things like, how can we integrate new transportation options like Uber and Lyft, for example, into existing systems that are consist of ordinary cars and buses? And how, for example, might we make these new mobility opportunities, these new mobility options, function more collaboratively with the old systems? How can Uber and Lyft compete more productively with public transit? So in the course 155, we try to furnish students with the tools to answer questions like this, but we also try to teach them ways of abstracting problems, meaning we try to teach ways of thinking about the problem so that the problem can be solved. Now, much of the course is devoted to two issues that have very different sorts of solution methods. We might call these two methods, or these two issues, demand and supply, which kind of makes it sound like it's an economics class, but it really isn't. When we're talking about demand in the transportation context, what we're really interested in is formulating and using statistical models to forecast how many people will want to use our transportation system, whether we're talking about a bus system or a rail system or whatever. And how are these human loads on the system going to change over time, say from one day to the next, or from 1 hour to the next? Or maybe we want to predict what the kind of modes people are going to take when they commute to work. How many people are going to drive? How many will take the bus? How many will ride their bikes, for example? What we're dealing with in this aspect of the course is human behavior. And of course, there are no physical laws governing how people make choices about how they travel. However, there are some very rudimentary economic theories, and we can use these along with a field of science called econometrics to make some rather sophisticated forecasts about the human loads on the transport system. Now, the second element of this course we could call supply. And here in this element, we're concerned with the infrastructure. And the infrastructure might be the roads or the metro lines, or maybe it's a nationwide network of airports. We're specifically interested in how well this infrastructure is performing when the infrastructure is subjected to its human loads. In other words, its demands. So for example, how long might people have to wait at a bus stop if we change the bus service? Or how bad is traffic congestion going to get in our downtown if next year we add a lot of office space and a lot of office buildings? There's a lot of elegant theories we can use here to address these questions. But the thing is, there's kind of a challenge when we're using these demand and these supply side theories. And that's because demand models, they predict the human loads on a system, but these loads depend on how well the system is performing. Think about that for a minute. I mean, if we had a metro system that was very unreliable and very expensive to use, then in this case, not many people would use the system. So imagine people for a second who kind of work on the demand side of the problem. And suppose in effect, they go to people who are interested in the supply side of the problem. And they say, hey, supply people, can you give us your predictions as to how well our system will be performing? And the supply side people ask, well, they answer back, they say, well, we'd like to help you with this, but in order to predict the performance of the system, we're going to have to understand the demand for your system. And that makes sense, of course, because think for a moment, for example, when systems get really crowded, they don't perform well. So what I'm trying to point out here is there's a real dilemma we have to deal with. We're kind of chasing our tails. That's because the outputs from a demand model are needed in the supply models. And the same is true in reverse. The outputs from supply models are needed for the demand models. what we have here is something called an endogeneity problem, and there's lots of nice theories for dealing with this. But that brings us to a point I really want to make about the class. Although the course deals in a great deal of theory, everything about the class is very practical. Because everything we talk about in the class are ideas that can and should be deployed and tried in real world situations to solve real world problems. Now, to underscore this point, the class has a weekly laboratory session. And over the course of the semester, what students do in the lab is they perform something called an environmental impact study. And what that means is we imagine that there's going to be a large new development, like, for example, a new shopping center that goes into some city somewhere. And then what the students do is they determine, first of all, what is going to be the added demand for travel as a result of this new development. And then they assess what that extra demand, how that extra demand is going to impact traffic congestion nearby. And then finally, they look at engineering solutions on how they might mitigate that congestion. So the laboratory project that they work on over the course of the semester every week demonstrates to students how the theories that we learn about in the lecture can be applied to solve real world problems. And together, just in summary, what I'll say is that the lectures and the lab for this class, in combination, they seek to achieve two things. First, they want to introduce students to the very best ideas that transportation engineering has to offer. And that's because we want to stimulate student interest in the field. And second of all, we want to give the students the best foundation possible to make them appealing to to employers when they begin their professional career, and to help ensure that their career will be marked by a lifetime of positive contributions. So that's really all I wanted to say about the course. Maybe now what we can do is return to, see if we can return, how do I, I'll stop sharing. What do I do next, Julia? Stop, there it is. Okay, good. Sorry for the, I haven't taught remotely in a few months, so I forgot how to do it. We have Karen Nelson with us. Professor Nelson, hi, nice to see you. How would you like to go next?
That's fine. I have no idea where you're at in the program.
You are our queen of the hitter, let's say.
Awesome. Let's do it. Hi, everyone. I'm just coming from the classroom. I was just teaching a graduate class. And so I just ran back to join you. So I've missed the beginning portion of this, but it's great to see so many of you here curious about our program. So should I just launch in? Gotta share my screen now. So the class I wanted to tell you about is called Water Systems of the Future. And it is an undergraduate class that I teach. All right, can you see it now? And is it in like the right presenter mode?
Looks pretty good to me.
Cool. So water systems of the future. Why might you be interested in this class? Basically, everything depends on water. So, you know, I'm in our environmental engineering program, but water is not only important to environmental engineers. So hopefully, no matter what area of civil and environmental engineering or engineering at all you think you might be interested in, this class is designed to pretty much give everyone and anyone who has an interest in water the basics you need in order to be like a proactive and active citizen in managing our precious water supplies. So most of us in the US take for granted the fact that you can turn on your a tap anywhere at home or at work and clean, safe water, drinking water will come out of it. And that is because our engineers have built this incredible water infrastructure. So this image right here is basically the human water cycle or the engineered water cycle. So you probably are familiar with the natural hydrologic cycle where water evaporates from the oceans and then rains on land and runs back into the ocean. replenishes our aquifers. But because we have so many people on this planet, we can't just rely on the natural hydrologic cycle to provide sufficient quantities to our human populations anymore. So we have developed, in particular in this country, massive infrastructure to supply adequate and safe water to our human populations. So it's taking water either from the groundwater or from lakes and rivers and delivering it to our populations. And then when you flush the toilet, most of us have the privilege in the US of not really worrying about what happens next to that water. That's actually not the case in a lot of the rest of the world. Many people have tap water that they turn on the tap and the water's not coming out of it a lot of the time, or they may not even have to have a tap. They have to go and collect their water manually. And then they know exactly where their waste goes because they see it in the environment. It doesn't just disappear in a pipe and get taken away. So my point in bringing this up is there's a lot of important work to do in bringing just basic services to people and populations throughout the world that don't have access to this incredible infrastructure that we have in the US, but it might need to look different. So just because we have systems of delivering water and treating our waste in this country, it doesn't mean that they make sense everywhere. And it turns out that the infrastructure we have in the US is actually, it was never designed for the current environment that we live in now, where energy is expensive and it generates greenhouse gases. And then because of the climate change that's already occurring, our water supplies are becoming less reliable and more scarce. And so we can no longer rely on our water infrastructure that, the current infrastructure that we have to adequately address the challenges that we're facing, which are compounded by our growing populations. I already mentioned drought and climate change. We've got sea level rise. Many of our facilities are located right at sea level. We have different types of challenges in our mega cities than we have in our rural populations. And then even in California, we have unimaginable wealth, and then we have heartbreaking poverty. And we don't have what I would call water justice in the state of California, where everyone has access to high quality and safe and affordable drinking water. And if you pay attention to California politics, you know that there's also a lot of conflict between our agricultural sector, which also needs a lot of water for irrigation, and then the demand from our urban population centers. So basically, there's no better place to study water than California, because we have all of these challenges that are sort of representative of challenges that the rest of the world faces. So in this class, we talk about all of that. And one of the principles that we talk about is how can we take advantage of the fact that water in theory is infinitely recyclable? We know that from the natural hydrologic cycle, but how can we design our engineered processes rather than using water once and then discharging it? How can we mimic that infinite recyclable process of the natural hydrologic cycle? How can we do that in our engineered systems? And so this is a schematic we talk about a lot in the class. On the left-hand side are illustrated all the different ways that we use water. And then instead of just discharging it after that, we talk a lot about this principle of resource recovery, where we can recover the water. We can actually recover energy from our water in the form of heat and in the form of organic matter that we can use to produce energy, and we can recover nutrients that we can use for fertilizer. And we can do this all in a very energy efficient way and using renewable energy resources. So it's just one specific example. We can now turn wastewater directly back into drinking water. And this is actually my son at an exhibit at our local science museum, the Exploratorium. If any of you are from the Bay Area, you might have visited it. And he's not actually drinking wastewater. This is just a museum exhibit, but it illustrates this principle that we actually implement in California now, where we apply many, many, many different treatment processes to make wastewater safe to drink again. So this is me actually drinking purified wastewater at a facility down in Orange County. And the way we can do this is by using a lot of different treatment processes. We can use ozone, we can use activated carbon with biological degradation, we can use membrane microfiltration, we can use reverse osmosis, we can use hydrogen peroxide and ultraviolet light to achieve advanced oxidation and remove all of the pathogens and organic chemicals that are of a concern. So that's just one example of innovation. And you also know California is the heart of innovation. And so in my class, what we talk about is, what are our water systems of the future going to look like? What do we want them to look like? And how are we going to get there? And I've sort of emphasized technologies, but we don't just talk about technology. We talk about policies and politics. We talk about the role of climate change and the intersection with energy. And we talk about pricing and finances and affordability. And we talk about water justice. We talk about how we can be leveraging big data. And the overarching theme is innovation. And my goal is that you become a water change maker by the end of the semester. And I'll leave you with an inspirational quote. Anyone who can solve the problems of water will be worthy of 2 Nobel Prizes, one for science and one for peace and one for science, by our former President Kennedy.
Thank you, Cara. Thank you very much. So, to everyone in attendance, you've now had a chance to see a sample of the kind of courses we teach at the undergraduate level. These were only a sample. There are many more courses we offer. This gives you an idea of some of the interesting things we try to tackle and the breadth we try to expose our students to. At this point of the presentation, I'm wondering if any of you have any questions. Maybe you have questions about a specific class or something more general about classes or the undergrad program, whatever might be of interest to you. We have a few minutes now. If anyone has a question, they want to shout it out or send it out via chat. This would be a good time.
Oh, hello.
Hi.
Dr. Hussey, my name is Mahali Samuels. I'm in Santa Monica College student, and my major is environmental engineering, obviously, as I'm here. I have lots of questions. So for the people that can answer more of a short question, to you, for your transportation course, would you suggest some prep courses to have an understanding better for, like, with your course, like with statistics, psychology, and economics?
You know, I think a good grounding in physics and math is probably what's most important. We deal with probability, and a course in probability and statistics is fine, but if not, we can deal with that then when it comes up.
And my second question to you is, because you do with transportation, how do you tackle something like, what I'm interested in is urban restoration planning. So, you know, where there are bridges and highways that disrupt the migratory patterns of animals, little things, turtles all the way to deer and elk and whatever. Is that something that we would learn in this class or tackle with this kind of field?
Well, you're dealing with a kind of a multi-dimensional problem here, multidisciplinary problem. So certainly in 155, for example, you'd learn the tools to see about what the impacts are. You'd also learn certain mitigation strategies, but those mitigation strategies are targeted mostly to the transportation infrastructure, fixing the roads, adjusting the bus routes, whatever. But the other courses we offer, environmental engineering, for example, energy and climate change, could address more of the environmental restoration efforts. But I don't think any one single class we offer might address the things that you're interested in, but I think a suite of courses that we have could collectively satisfy some of your pursuits.
Thank you,
Does that make
Dr.
sense?
Yeah, that makes sense. Thank you, Dr. Cassidy. I guess I would follow up to Dr. Stacy. I was asking for climatology, would seem like a good prep course be a geography or geosystems and geology type course before transfer, or just wait till we get to UCB and, jump in?
So any preparatory courses that introduce you to climate change broadly would set you up for the topics that I described, but there's not going to be hard prerequisites on that.
Mhm.
We'll try to build what we need into the course itself, but that context will be valuable. So these could be sort of, any global atmosphere physics, atmosphere or oceans types of class, or a carbon cycle class. Anything that kind of focuses on those global cycles will give you that perspective. And then the course I was describing will kind of take down into sort of thinking about the local impacts of that global change. But we'll build up some of that global perspective as well, just at the start of the class.
Thank you. And for the two other professors, I have questions. I'll start with Dr. Nelson. Dr. Nelson, you're talking about water systems. I think it's super important. And I forgot, I don't know the percentages, but I know our groundwater percent is very low. And then compared to our oceans and other sources, how do you feel about all of the dams that we have globally and the impact that it has on the earth and stresses for the planet and also for the ecosystem?
That's a great question. And it's a bit easier to answer for the context of California than I think for the world in general. I think in California, it's really unlikely that any more dams are going to get built. And in fact, some of the dams that we already have are going to get taken down. So there's studies being done, for example, on the Klamath River, where the benefits that we're getting from the existing dams, which the two main benefits that matter in California are storing our water, but also the hydroelectricity. But there are certain dams that no longer provide enough benefit, to make up for the ecological consequences that you've mentioned in the ecosystem degradation. So I think we're actually entering a period of dam removal in California. That's not necessarily the case in the rest of the world. There are other countries and regions that never went through a big development phase where they built large dams. And so all of those projects are highly controversial, but it's possible that, there still may be forces that lead to the construction of more dams. But the research in California is basically about optimizing the performance of the existing dams that we have, and then on dam removal.
Wow, that's positive. Yeah, you're all wonderful. And to my last professor to ask a question I hope I say your name correctly, Dr. Zikos? Zach, please. So I'm so fascinated in geotechnology now and what you're talking about in soil science and how it's different than, the seismology and the geologists, because they go deeper and they love rocks, really, really rocks. Okay, so you talked about sinkholes and found station structures and pipelines and water networks, which goes back to Dr. Nelson's course that ties in. What do you think about, basically, the Millennium Tower in San Francisco? How did that kind of go wrong? Like, where were the geotechs with that? Or is that it was okay and then some other things happened and it started to sink or tilt? And as engineers, like, how do we not let those things happen?
Yeah, thank you for your question, for participating today. With this, even though there's litigation on various aspects, there is definitely an underlying concept that everybody agrees on in terms of something that went wrong in the geotechnical design. There was, I think what happened, and we had a seminar speaker actually presented really well last week in our program, which is another great benefit that you would get in this department. There are a lot of great speakers that join weekly seminars that really serves as an addition to a lot of the classes that we teach and really brings the tie with the industry. But he was with one of the companies involved. And what happened basically is that this building basically was being built in an area that has supported similar buildings in the past and similar ground conditions, similar foundation styles. And so there was higher confidence from the engineers in moving forward with some of the traditionally used approaches and techniques, and not extremely thorough soil investigation and soil testing, because we could depend on some of the information from neighboring structures. And what was different about this building is how heavy it is because of the different type of construction. And therefore certain materials, soil materials deeper below experienced stresses that were higher than basically anticipated in the original design, which led them basically to compress and settle in larger amounts than it was again anticipated from the original design. So, and as I said, this is the part that everybody agrees on. There are a whole bunch of other issues that we don't have to get into right now, but I think it goes to speak to something that I am very passionate about when it comes to geotechnical engineering, is this natural variability of the materials, and therefore no two projects are ever completely alike. But also demonstrates the need for monitoring, for characterization of the subsurface conditions, especially as we try to deal with a lot of the natural disasters, climate change impacts and whatnot. And I think this is something that just keeps me excited about this field of always trying to do our best to characterize something that we can't fully always, penetrate and get samples from every different location.
Thank you, Dr. Nelson, for your very tactful and diplomatic explanation. And thank you to all of the other doctors and professors for answering my question.
Thank you, Nahaya, for your questions enriching the event. Thank you very much. Who else would like to ask a question or two?
And you're also welcome to put them in the chat.
Yes, absolutely. There's a chat question here, I think. Let's see.
There's a hand up. Catalina?
Yes, thank you. Hi, my name is Catalina, also from SMC. I'm basically just going through a consideration of different majors at the moment, but these are two majors that I'm really interested in. But I would like to ask, what are the key differences that you think a student should consider between choosing between these two majors, like the key characteristics of them?
Which two majors, Catalina?
Oh, between the environmental versus civil engineering, I mean. Sorry.
Mark, why don't you take that one?
The beauty of Berkeley is that there's no difference.
At the moment.
At the moment. So we're all kind of smiling and chuckling because we are in the middle of a conversation about exactly a topic related to this. At the moment, we only have one major in our department. Our civil engineering major is a broad integrative major that spans the civil disciplines and environmental. And you'll have that breadth of experience upon graduation. We are actually currently exploring the possibility of developing a second major in environmental engineering. But that is, given the timelines of things at Berkeley and at UC, will probably not exist on your undergraduate timeframe. And so for your experience, you'd be looking at this broad degree, which spans civil and environmental engineering.
But Catalina, maybe I'll jump in and mention, should you decide to join the program, and after you're here a semester or so, you'll only be here a couple of years, so you have to think fast, but you might find you're more drawn to the civil side of things or more drawn to the environmental side of things. And if you should come down one way or the other on that equation, you could emphasize and take more courses in that area at the expense of the other. So you are allowed to choose a curriculum for yourself that caters to your interests and your professional goals. So although we don't have an environmental engineering degree, you could get a civil and environmental engineering degree, for example, that has a pretty heavy emphasis in environmental, or not, depending on what your interests are.
Oh, thank you. I was a bit confused about that distinction because I know a lot of universities like separate those two. And I kept like looking at the website and got confused.
We're
But thank
laughing too because we're a little confused about it ourselves, but we're trying to sort that out, figure out what we want to do.
I see Miranda's hand is up, and then Jacob.
Oh, okay. Miranda? Oh, sorry. Miranda, were you next?
Yes, hi, professors. Thank you all for your time today. I'm hoping that any of you can speak to any specific experience you have either admitting, advising, instructing, or mentoring older students, full-fledged adults, if you will.
Julia, what do you think?
Sorry, had to find my mute button. I would say we definitely have some students who are junior transfers usually who are perhaps not your standard 20-year-old age. And thank you, future students. And I would say that for the most part, I have seen these students, come in and become a part of their class and become leaders often in their class. They're often more directed than maybe someone who's 20 years old, and they tend to do well. So it's great. I think it's a wonderful thing to be able to go to school at whatever age you might be.
Do you find then that there is a lack of bias in looking at those applications?
Oh, age, we won't even look at age. That we wouldn't even know it. I mean, maybe we could be inferred from statements or something, but that isn't even a consideration.
That's exactly what I needed to hear. Thank you so much, Dr. Cassidy.
Sure. That's a great question, though.
And then Jacob had his.
Were you next?
Yeah, how's my audio? Could you hear me?
Yep.
All right. So apart from all the classes and curriculum that we have to take, I understand that a lot of engineers, especially four-year colleges, want to have experience outside of school and participate in internships or opportunities like such. I was just wondering, is there anything like at UC Berkeley, any programs that help us get internships and stuff like that?
Yeah, Julia can maybe speak of the internships. But I also want to mention we have what's called an undergraduate research opportunity program. So for junior transfers, they can jump into it as soon as they join us.
That's great.
Have a chance. First semester, you take a general kind of seminar course on the philosophy of research, and then in the second semester, you team up with a faculty member and his or her grad student, and you work in that shop pursuing research. Ideally, the end result after a few semesters of doing that would be some sort of publication. Now, our students also get internships, say summer internships, for example, and Julia, I think, again, is an excellent person to speak about that.
Yeah, so there are so many things to get involved with within our department and within our university. So the American Society of Civil Engineers is very active in our department, and every week they bring in companies to do an info session and to tell students about what work-based that specific company does. And they're there because they're trying to recruit our students, and they're looking for interns for the summer. They're looking for people to hire as they graduate. We also host 2 career fairs, one in the fall and one in the spring. And there's just all of our teams, our competition teams to get involved in. And there's just all kinds of ways to make connections and to find those types of opportunities for growth.
Okay.
But lots of our students do summer internships.
Oh, most of them, yes.
Yeah, through the networks here, or sometimes on their own, but often we can open doors for students within just various professional firms and so forth.
Yeah, that's great to hear. Thank you so much.
Anybody? How about another one? Well, I think then that's going to bring our event to a close. Again, thank you all very much for attending. we really do hope you consider joining us. Drop us a line if in the coming weeks you have other thoughts or questions you might have. Shoot us an email. We'd be happy to carry on the conversation.
Thank you so much, everyone. This has so reinforced my decision path.
Success.
Thank
Thank you.
you.
Thank you. Well, have a great day, everybody.
To everyone.
Thank you again. Goodbye.